In my last video about binary trees, we talked about how if a tree is unbalanced, it can ruin the time complexity for search, insert, and delete operations. So in this video, we'll be talking about AVL trees, which are a type of self-balancing trees that balance the tree as you insert/delete. They do so by going from the bottom and then going upwards. And by doing so, they can guarantee that the three aforementioned operations will be done in O of log n time complexity. So let's talk about that. AVL balances the tree by rotating it. For example, if we have a tree that looks like this, in this case here we clearly have a tree that's unbalanced. Remember, a tree is considered unbalanced if the difference in height between its children exceeds 1, or if either one of its children are unbalanced. In this case here, we have a node here that has a left child with height 2 and a right child of height 0, so the difference in height becomes 2, therefore it is unbalanced. And AVL would fix this by rotating it to the right, like so, and it would become like this. Now, AVL actually has 4 different cases in which it has to cover rotations. I won't get into that just yet though, because we need to talk about how you would even do a rotation to begin with. Now, with this example, it seems fairly obvious, but what if we have something that looks like this? Let's write that up real quick. And there we go. So something like this. What would happen here? Now, in this case here, if we just rotate, right, we have a case like this, but then where does the 2 go? Because when I rotated this over in this direction, this 2 kind of just got left somewhere in this area here. Now, the way I've always liked to view rotations in AVL is to view them as chains. And to do so, I like to use paper clips. Alright, so right here we have a set of paper clips, and we're going to treat these paper clips as a tree. And what I'm going to say is that at every point where these paper clips meet is a node, and then these paper clips themselves are just kind of like that line from a parent to its child. So let's just give these some values here. Let's say this node here is 50. Say this one is 60. This is 25, 20, and 30. And I know this tree isn't imbalanced, but I just wanted to show a standard rotation. This is going to be a rotation in this direction, so a right rotation. Right? And if I want to rotate this, then what I can do is, if I pick up this right here, and I lift it up, then everything right here will drop down, and you kind of get something that looks like this. Right? So I just picked this up, and everything came down, and the value shifted down as well. Of course, if we do this, we notice there is one problem, and the problem is this right here means that this node right here has 3 children, and we can't have a node with 3 children in a binary tree. So this has to move somewhere. Well, then we can just apply logic and we say, well, since this value here is greater than this value, then it must go into this tree here. And then this value is less than this value, so it must go right here. Right? So all we have to do is then just move this and move it right here. So if I were to do that, I'm going to do that real quick. Now we get something that looks like that. And I've always found that using paper clips can help visualize that moving motion. And hopefully this helps visualize it for you guys. And let's go back to the drawing board. Alright, so we'll come back to this problem again. If we want to do a right rotation here, then we pick up the tree by the 1. So if we pick it up like a link, like this, the 1 comes up to the top. And then the 0 will fall off to the left. And then the 3 will drop over to the right. And the 2 will be left somewhere in the middle here, kind of hanging. Now obviously this isn't an actual binary tree because no node can have more than 2 children. So this 2 will have to move somewhere. In this case here, it's greater than 1 and it's less than 3. So the tree rooted at 2. Now remember, tree rooted at 2 means that there could be more children here. I've only chosen to show the root of this tree. So the tree rooted at 2 will be moved over, so it becomes the left child of 3. Now, we know for a fact that 3 doesn't have a left child in this instance. It has an empty spot for 2 to fit into, and we aren't overriding anything. And we know this because back at this tree up here, the left child of 3 was the tree rooted at 1. However, when we did this rotation, 3 lost its left child because 1 became its parent up here. So because of that, we know there's an empty space and we're not overriding anything, and we can freely put the tree rooted at 2 here. So that's how you would do a right rotation. For a left rotation, it's largely the same idea. So let's do an example of a left rotation real quick. So it's basically the same tree again. I just mirrored it. And in this case here, the right child is heavy, right? Because it's unbalanced right heavy. We want to do a left rotation. So we pick up the tree at 2, and then 0 falls to the left, 3 falls to the right, and then the tree rooted at 1, it can't be here, so it's less than 2, greater than 0, so it'll move over here. And for the same reasoning, 0 doesn't have a right child anymore after that rotation, so 1 can go there. So that's how you take care of rotations. And now we can talk about the actual cases that AVL has to cover for rotating. So what are the 4 cases that AVL must cover? Well, those 4 cases are the left-left case, left-right case, right-right case, and right-left case. Now, the first word of these cases, so the first direction, refers to which child is heavier. So, for example, if we look at that previous example we used before, this would be left case. Now, as for the second word, that part's a bit more difficult to explain, so I'll explain that later when it makes more sense. But for the time being, just focus on that first word. So in this case here, we know this is a left case. It actually turns out this is it's called a left-left case. And just ignore the second word again for the time being. And as you guys saw earlier, this is actually fairly easy to fix. You just do a right rotation, and therefore we get 2 as the root, and 3 and 1 is children, and this is balanced. However, just because the left child is heavier, a right rotation doesn't necessarily fix it. So let's come up with an example for that. So let's say we have a tree that looks like this. Now, if we do a right rotation here, because it's still left heavy, well, we pick up the 1. So 1 comes up to the root, 3 drops down to its right, and then the 2, well, the 2 doesn't go on the left of 1 because, first of all, 2 is not less than 1. And second of all, when it was over here, the 2 is not the left child of 1, it was the right child of 1. So 2 would actually go where it went before, like so. Just this time we don't have a 0 on this side. Now you guys will probably notice that in this case, we still have an unbalanced tree, right? It's just this time instead of being left heavy, it's right heavy. And so this right rotation didn't fix anything. And we can't just do another left rotation because if we do that, well, we just end up getting that tree. So we'll just end up just rotating back and forth. So that clearly doesn't work. So why does this happen? Well, in this case here, this one's actually known as a left-right case. Left-right case. And this is because the left child's right child has a height greater than the left child's left child. So if that happens, then it ends up being a left-right case. So let me write that out real quick. Happens when left's right height. Now this one, there's a bunch of apostrophe S's here, so hopefully you guys can bear with me here. Is greater than left's height. So when this happens, then it ends up being a left-right case, and you can't just solve it by a simple right rotation. To fix this, well, if we have the left-right's, so remember 1 being the left-right's height is greater than left-left's height, well, we can fix that just by rotating this part here, just this tree, to the right. Because if we do that, remember, basically what ends up happening is this one has its height shrunken, and this one has its height increased, because this rotates down and this goes up in this direction. So you kind of have like a reverse effect, right, where this height goes down because it gets shot up a bit, and then this height's increased because it gets pushed down. And if you do that, then it will fix. So let's actually try that. We rotate let's actually do this in a step-by-step basis. So if we rotate the left child first, then we get 3, then 2, then 1. And this rotation is just any standard rotation you would see. So if we have like a child here, you guys learned how to resolve that just a moment ago. So just a standard rotation, and then we do a rotation this direction. Now we get 2, 3, 1, and we get a balanced tree, right? So you can imagine this kind of as a corrective rotation, and then you do your major rotation. If you notice, we still do our major right rotation, but we just make sure we do our little corrective rotation first. All right, so that is that. And so if we want to look at this second word then, it basically refers to if we have the left's right height is greater than left's height, then we call it left-right because the left's right's height is greater than left's, right? So we focus on this part here. Now, in the left-left case, what we had earlier is basically the opposite of this. So left-left happens when, now, remember, the opposite of greater than is not less than. The opposite of greater than is actually less than or equal to. So we've got to change it to less than or equal to. Left, right. So there we go. So those are our 2 cases. And for the right case, it's basically same thing but mirrored. The only thing you guys really have to watch out for is to make sure that we maintain the correct comparison operator here. So for example, when you're doing your, let's just draw up like a little arbitrary tree here. Right? So in this case here, we have a right heavy, so the first term is right. What you're comparing is the right's left greater than the right's right? Not greater than or equal to, but right's left is greater than the right's right. Basically the opposite, right? You go right, then left. Another way you can look at it is you always pick, if the inner side has a height greater than the outer one, then you got to do a corrective fix. Right here, the inner side had a height greater than the outer side, so we had to do a corrective fix. So that's one way of looking at it. All right, so now let's talk about why this works. Let me erase this, and we can talk about that. So why does AVL balancing work? Well, for the time being, let's just limit the explanation for the case where the left child is heavier, just to keep things simple. It's the same for the right child case, it's just mirrored. Now remember earlier at the beginning of the video, I said that AVL works by balancing from the bottom up. That's something to keep in mind. So let's say that V was the first unbalanced node that we found. First unbalanced tree. And let's say that Y, in this case here, has a height of H. So I don't know how many nodes could be beneath Y, just that the tree rooted at Y has a height of H. And let's also say that this tree is left heavy, so it wants to do a right rotation. Okay. With Y having height of H, we can actually determine what the height of Z is. Or rather, we can limit what the height of Z is. Since we said that V is the first unbalanced tree, and we move from the bottom up, that must mean that X and Y and Z must be balanced, because if they weren't, then they would be the first unbalanced tree. If X is balanced, then the difference in height between its two children cannot exceed 1. So therefore, if Y's height is H, then Z's height must be either H minus 1, H, or H plus 1. Because it can only be within 1 of H. So now let's do a right rotation. So if I do a right rotation here, then this results in X being the root, V being the right child, and W keeps being the right child of V. Y becomes the left child of X, and Z becomes the left child of V. Now, Y still has its height of H because nothing's changed about its tree, and Z still has its height of H minus 1, H, and H plus 1. However, this time, though, X's right child is not Z anymore, it's the tree rooted at V. So what is the height of V then? Well, V's height must be 1 plus Z's height. Now, I'm not going to go through the entire formal proof, so if you notice, I'm kind of disregarding W. You can think about it more if you want, but I didn't want to go into an entire formal proof about this. Okay, so if V's height is just 1 plus Z's because, well, it's just adding one more node on top of Z's height, then its height must be either H, H plus 1, or H plus 2. All right, and hopefully that makes sense. You're just adding 1 to each of these three options here. Now, if V's height is H and Y's height is H, then X is balanced because they're both the same height. And if V's height is H plus 1 and Y's height is H, then it's still balanced because they're within 1 of each other. But if V's height is H plus 2 and Y's height is H, then it's unbalanced. So of the three different cases, one of them results in an unbalanced tree. And that one case is if Z's height is H plus 1. Because if Z's height is H plus 1, then V's height becomes H plus 2. Those are linked together. So the only case in which just doing a simple right rotation doesn't work is if Z's height is H plus 1. Right? Therefore, if we look at this again, H plus 1, H. So the only case that we have to do a corrective fix is if Z's height is greater than Y's height. And that's kind of why, if we look at the previous examples that we did, we have a left-left case and a left-right case. If Z's height is H minus 1 or H, in other words, less than or equal to Y's height, then it's just a simple right rotation. It's just a left-left case. But if Z's height is greater than Y's height, then it becomes a left-right case. We have to do a correction first. So this is kind of like an intuition as to why this balancing stuff works. So hopefully that helps. And let's move on to insertion and deletion. All right, so let's cover insertion first. Now, it's actually fairly simple to do insertions now that you guys understand how the rotations work and the different cases. Let's say we have a tree here. In this case here, the tree is balanced. Now remember, AVL will balance as you insert into the tree. So you should never have a tree that's unbalanced that you're inserting into, right? If you inserted into it previously, then AVL would have balanced it first. So when you want to do your next insertion, it's already balanced and ready for you. And AVL only works if it's kept balanced as it inserts and deletes. So in this case, we have a balanced tree. Now let's say I want to insert 5. Right? So this is just standard BST insertion. 5 is greater than 3, less than 6, greater than 4. So it goes here. Now, when you do this insertion right here at 4, you're going to check, okay, does inserting at if we just focus on this tree here, none of the other stuff, so 1, 3, 6 don't even exist right now. If we just look at the tree at 4, when we inserted 5, did that result in it being unbalanced? Clearly, no. And then we move upwards. Like I said, it checks from bottom up. Then we look at 6. Did this result in an unbalanced tree? Yes. So here is where we want to do our rotation. Yes, 3 has become unbalanced. However, because we're going from bottom up, 6 became unbalanced, so to speak, first. So we want to actually do a correction at 6. Now, if we look at here, it's left heavy. Now, what case is it? Well, left heavy, like I said. And if we look at the left child, its left's right child has a height greater than the left's left child. So this is a left-right case. So if we want to do a corrective fix, we have to do a left rotation here first. So then this becomes 3, 1, 6, 5, 4. And then now that we have this, now we can do our overarching right rotation, which will result in 3, 1, 5, 4, and 6. And now the tree is balanced, right? So if you notice, we don't have to balance 3 anymore because we already did our corrective fix and we did our rotation right then. So that would be how you would do insertion. Let's do one more example just to make sure we understand how everything's working. So let's try, let me think. All right, so let's try inserting 9 into this tree. Okay, so if we insert 9, 9 is greater than 3, greater than 6, greater than 8, so it goes here. And now when we insert it here at 8, then we want to check, okay, is this unbalanced? Well, clearly not. Then we move up. Is this unbalanced? Yes. So this is unbalanced. We check, well, it's right heavy. And the right's left child does not have a height greater than the right's right child. So this is a right case. So we just need to do a really simple left rotation. So this becomes 3, oops, that's not 3. 3, 8, 6, 9, 2. And we are good. So this has been balanced, and that was actually really simple because it was just a right case. And since you guys already understand rotations, then you can see that insertion is actually pretty simple. So let's talk about deletion. Now I'm going to go a bit into how to delete from a binary search tree because I'm not sure if you guys would be 100% familiar with it. We have a binary search tree here, and let's say we want to delete the value 7 from this tree here. Now, I can't just erase 7 here because that would just leave an empty spot. And I have to take something that's already into the tree and we put it there instead. Because I can't take something that's not in the tree. Otherwise, that would be inserting new data into the tree. So the question is, what do I put at this spot right here? Now, there's a couple constraints of the value that goes here. Number 1, all values to the right of this value have to be greater than or equal to it. And all values to the left of this one have to be less than it. Right? Because that's how the binary search tree would work. Now, most common strategy you see is to pick the largest value in the left tree. Or rather, the rightmost value in the left tree, which just happens to be the largest. It's because, obviously, if you're in the left tree and you go to right as far as you can, since right's always going greater than, then the rightmost value would be the greatest value in the tree. But why pick the left tree then? Well, if I pick anything from the left tree, then anything in the right tree would be greater than it by that nature, because anything on the right is greater than, anything on the left is less than. So that would satisfy the first constraint. Any value I pick from here would be less than any value here. Now, if I pick the largest value in this left tree, then that value must be greater than all the other values here by definition. So that would satisfy both constraints then, because if I pick the largest value in the left tree, that largest value is going to be greater than all the values on the left, and it would also be less than all the values on the right. So, in this case here, the rightmost value is 6, which is the largest value in this left subtree. And so what I would do is I would put this 6 where 7 is. Now, that doesn't mean I can just erase the 6, because let's say 6 had another child, 5.5, right? Then I'd have to do the same thing. It's kind of a recursive delete, where wherever I move and replace from, I have to go here and also do that same delete. I have to find the largest value in its left tree and put it there, and go down, so on and so forth. So you can't just immediately just replace. Right? You have to properly delete this. Now, once I delete the 6, of course, in this case here, there is no left child, so I just delete that. I then have to check, starting from wherever I've been deleting from, is it balanced? Because deleting can often cause imbalance issues. So right here at 5, well, there's no balance issue there. So I move up and I go back up. Right here, is there a balance issue? Yes, there is, because the right child has a height of 3 and the left child has a height of 1, which is an obvious imbalance. So in that case, this is just back to the standard 4 cases that I've covered just previously. In this case here is right heavy, right? And if you notice here, then it's right heavy, and then the left, actually let's make this a little better. Let's actually put 10 here. We'll make it a little more interesting, essentially. 8 here, 9 here. So let's say this is our tree, right? In this case here, the right child is heavy, and the right's left child has a height greater than a right's right child, so we need to do a corrective fix first. So in this case here, we need to do a tiny little right rotate. In this case here, right rotate will result in 8, 10, 12, 9. So this would be our resulting tree, so we'll put that there. 8, 10, 12, 9. And now that we've done our corrective fix, we can do our large left rotate. So we do a large left rotate, will result in, well, I pick up the 8. So 8 comes up to the top. 6 and 5 go to the left. 10, 9, 12 go to the right. And that's balanced. So just replace that tree there. 8, 6, 5, 10, 9, 12. And then we go up to the top of the 4 and check if that's balanced, and it's balanced. And since that's the root, we are done. If we notice, we have a perfectly balanced tree with the 7 removed. So that is insertion and deletion, and that's really all you really need to know for AVL trees. So hopefully this video helped, and if you guys have any questions, you can leave in the comments below. Thank you.